We've talked about ionization energy a little bit in class, but we haven't given it a particularly good definition. Now, your book probably has a really complicated scientific definition in it, but I don't want you to worry about that too much. The definition that I want you to think about when we talk about ionization energy is what I put up here. Ionization energy is the amount of energy it takes to steal an electron from an atom. What does that mean? Well, atoms have all these electrons orbiting around them, and we're particularly concerned with the valence electrons. It's possible to remove an electron from an atom, but depending on the atom that we're doing this, it takes a different amount of energy to pull an electron away. Let's think of a good analogy. Let's imagine that instead of stealing electrons, we're interested in stealing purses away from people. Now, we've got two types of people, two atoms if you will. We have a weak old lady atom, and we have a big tough guy thug atom. We're going to have to put different amounts of energy into stealing away the electrons or the purses from these guys. Now, our little old lady, it's going to be very easy to steal away her purse. So we'd have to put a low amount of effort. So we'd say that there would be a low ionization energy. The tough guy, on the other hand, is going to require a lot of energy and a lot of effort. So if this is an analogy for atoms, we'd say that the tough guy atom has a very high ionization energy. You can think of ionization energy a lot like effort. As it gets harder and we have to put more energy into stealing something away, ionization energy is higher. As it gets easier and we don't have to put as much effort into stealing away something, we say that the ionization energy gets lower. So if we think about ionization energy like effort, we can come to these conclusions. We say easy to steal. If it's easy to steal away an electron, we have a low ionization energy, which I abbreviate just with IE here. Now, on the other hand, if it's hard to steal an electron away, we have a high ionization energy because we have to put a high amount of energy or a high amount of effort into pulling that electron away. Now, let's look at how this relates to what we've already learned about atomic size or atomic radius in the periodic table. So in class, we've learned a little bit about the sizes of atoms, and we've learned a little bit how to figure out the sizes, the atomic size, or the atomic radii of atoms based on where they are on the periodic table. Let's quickly review what we've learned so that we can fit it in together with what we learned about ionization energy. Now, the periodic table is divided into rows and it's divided into columns. And we've learned that as we go down each row, we add energy levels around the nucleus of an atom. Now, we've learned that energy levels are much more than just circular shapes, but I'm going to draw circles here because it's an easy way to understand the trends in size. So here's our first row, one energy level, which I'm going to show by one circle. As I go down, two energy levels, two circles, and finally go down to our third row. So what we can see is, as we go down the periodic table from top to bottom, the size of our atoms is increasing. And that's a general trend. Top to bottom, they get bigger. Now, on the other hand, something interesting happens. As we go from left to right, atoms actually get smaller. We talked about this in class. We're adding electrons as we go from left to right, but those electrons are still living in the same energy levels. They're not moving any further away from the nucleus. And what's causing the atoms to get smaller is additional protons are getting added, which pull those rings of electrons much closer. Let's take a look at this. If this were hydrogen here, let's take a look at helium. Helium, which has another proton than hydrogen, has its energy level pulled in a little bit tighter. So it has a smaller atomic size or a smaller atomic radius, even though it has the same number of rings here. Now, I'm not going to draw all of the atoms here, but I'll just do a couple diagrams to give you a general idea of what's happening. We go down here, we add a second energy level because it gets bigger. But as we go across, the additional protons pull these energy levels tighter. So although this is much exaggerated, the size of the atoms as we go across decreases because of that attractive force. And likewise, if we look at our third energy level, the same thing happens. The protons pull these energy rings in tighter. And again, atomic size is decreasing as we move to left to right. So we can say that our atoms get smaller in this direction and larger in this direction. Let's take a look at the general shape of the periodic table. We could draw a rough sketch of the periodic table like this. And here are our trends. Atoms get bigger this way and smaller here. Let's really sloppily separate the metals from the nonmetals. And let's now think about ionization energy. We talked about the old lady and the big thug. But let's think about stealing electrons from different types of people. Let's say there are two types of people and they've both got purses. The purses represent the electrons. We have a guy who holds his purse way out here. And because he has a very large atomic size, is dangling his purse way out. On the other hand, we've got somebody else who holds their purse very tightly. Now, which of these is it going to take more effort to steal away from? Obviously, it's going to take more energy to steal away from the guy who holds his purse really close to him. And because of that, we'd say that he has a higher ionization energy. On the other hand, it's going to be pretty easy to steal a purse away from someone who's just dangling it out here. So they're going to have a low ionization energy. So what we can learn is that the larger the atom, the more it dangles its electrons out, the easier it is to steal the electrons away. The smaller the atom, the tighter it holds its electrons in, the harder it's going to be to steal those electrons away. Let's incorporate this with what we've learned about the size of atoms from the periodic table. These guys up here are going to be the smallest, because it goes smaller in this direction, and it starts with smallest over here. So these are going to be the guys that have their electrons most tightly held in. It's going to take the most amount of effort to steal them away. Let's take a look at this. We can say that these guys up here are holding in tight. And we can say that these guys here are just sort of dangling their electrons. They're not actually dangling, but they're much easier to pull away because they're so far out. These guys are dangling their electrons. These, as we can figure out, are obviously much harder to steal away from. So these have a high ionization energy. And the metals over here have a low ionization energy because it's easier for us to pull the electrons away from their large atomic radii. If we look at this, we can figure out one final thing. Metals tend to form positive ions, and that makes sense when we think about atomic size and ionization energy. Since metals have larger atomic radii, and they have their electrons sort of dangling around, it's easier to steal them because of their low ionization energy. So they tend to form positive ions, K+, Na+, Ag+, Fe has a whole variety of positive ions that it makes because it's easy to steal their electrons. On the other hand, these guys up here, the nonmetals, who are holding their electrons in very tight, it's much harder to steal their electrons, so instead of getting stolen from, they tend to do the stealing and form negative ions because they gain additional electrons. So O2-, F-, Cl-, P3-, and a whole variety of other negative ions you've learned happen because of the electrons are being held in very tight. So that's why nonmetals tend to make negative ions and metals make positive ions because of what we've learned about atomic size and ionization energy.